Welcome back to Mr. K's Simplified Maths. Today, we're tackling an exciting and challenging problem using mathematical induction on a second-order recursive formula. Get ready to explore the world of sequences and proofs. A recursive formula is a rule that defines a sequence where each term is expressed in terms of one or more previous terms. It provides a systematic way to generate subsequent terms of a sequence based on earlier terms and initial conditions. Recursive formulas are especially powerful for describing sequences that might not be easily captured by a single explicit formula, such as Fibonacci-like sequences. A first-order recursive formula is a recurrence relation where the value of a term depends only on the immediately previous term. For example, Tn equals to times Tn minus 1 plus 3 with T1 equals 1. A second-order recursive formula is a recurrence relation where each term depends on the two preceding terms. For example, Tn equals 3 times Tn minus 1 minus 2 times Tn minus 2 with T1 equals 2 and T2 equals 5. Let's work through a question. A sequence Tn is defined recursively as T1 equals 4, T2 equals 48. Tn equals 8 times Tn minus 1 minus 16 times Tn minus 2 for n is greater than or equal to 3. Prove by mathematical induction that Tn equals to n minus 1 times for to the power of n for all integers n is greater than or equal to 1. We begin by verifying that the formula holds true for the initial values. Step 1. Prove true for n equals 1, n equals 2, and n equals 3. Substitute n equals 1, n equals 2, and n equals 3 into the formula to verify it. The first two verifications are for validating the initial values T1 and T2. The third verification is to check T3, the first term of the recursive formula. Note that the formula Tn equals to n minus 1 times for to the power of n must be verified for T1, T2, and T3. Next, we assume that the formula holds true for all integers from n equals 1 to n equals k. Step 2. Assume true for all integers from n equals 1 to k. That is, we assume that T1, T2, T3, and so on, up to Tk are true. Are you wondering why we assume true from T1 all the way to Tk rather than just focusing on Tk minus 1 and Tk? This will become clear in a moment when we discuss the proof for Tk plus 1. Now, our goal is to prove that the formula is true for n equals k plus 1, which means prove that Tk plus 1 equals to k plus 1 times for to the power of k plus 1. Starting with the left-hand side, Tk plus 1 equals 8 Tk minus 16 Tk minus 1 from the recursive formula. Next, substitute the assumptions for Tk and Tk minus 1. From the recursive formula, Tk is true only if both Tk minus 1 and Tk minus 2 are true. Similarly, Tk minus 1 depends on Tk minus 2 and Tk minus 3, and so on. For this reason, we must assume every term from T1 to Tk is true, rather than just the two preceding terms, Tk minus 1 and Tk. Now, replace 8 with 2 times 4 and 16 with 4 squared, then apply the indices laws. After factoring out for to the power of k plus 1, it becomes clear that the left-hand side is equal to the right-hand side. Step 3. By the principle of mathematical induction, the statement is true for all integers n is greater than or equal to 1. Second-order recurrence relations might seem daunting at first, but with the structured approach of mathematical induction, they become much more approachable. If you enjoyed this lesson and found it helpful, don't forget to like, comment, and subscribe to Mr. K's Simplified Maths for more exciting maths content. See you in the next video.